talk to us about what we can expect to see out of you guys in the etch and deposition technology world in the next couple of years, and how is that going to enable smaller, tighter line widths, all that kind of stuff?
Sure. So what's unique about Plasma-Therm when you talk to us versus any other etch and PECVD equipment suppliers is that we don't supply, our main focus is not the silicon world, where the name of the game is tighter geometries. Our focus market is what we call the specialty markets, which is all the markets surrounding the silicon chip. We do gallium arsenide, indium phosphide, we do MEMS, we do LED, gallium nitride. So we do all of these other technologies that are not always driven by the geometry as much as they're driven by chemistries, by the alloys that are being used, by other things, not necessarily just the line width.
Right. Go back 18 to 24 months. Put yourself back there. You're looking ahead 18 to 24 months. You got a technology challenge in front of you that's got your engineering teams working to solve. What was that challenge and how did you get through it?
Right. So in our technologies, in our focus markets, what you will see is similar issues like the mainstream silicon. For example, one of our key markets is wireless chips. So HBTs and HEMTs devices. And in that arena, those are gallium arsenide devices. One of the key steps is the packaging step, where they're drilling via holes from the back side after the wafer has been thinned to around 50-60 microns. So we help our customers develop the process to etch those via holes that become the contact from the back side, obviously in a controlled way, in a faster way. So if you look at what we have developed over the last 12 to 18 months, we've done significant improvement. Our etch rates are close to double than what they were 12, 18 months ago. And as a result of that, that improves the throughput, improves the productivity of the systems.
So we're transitioning slowly away from 300 millimeter to 450, right? There you have all sorts of issues, planarity being one of them. What other kinds of issues are you guys addressing at those larger wafer sizes, or are you sort of agnostic about that? It doesn't really matter.
To us, it doesn't matter in the sense that that's not our primary focus market. We're still, it's interesting because obviously the mainstream is the largest semiconductor portion of the market. But if you look at all of the other markets around it, there are markets that are still doing processing on 2-inch wafers. Majority of the LEDs that are being produced today are still being done on 2-inch wafers, 2-inch sapphire wafers. So that's the world we live in. So even though we carry similar challenges in terms of geometries and so forth, but we're doing them at a different scale. We're not directly involved in the 300 millimeter and the 450 millimeter markets.
So can you talk about LEDs a little bit? I know a little bit about the technology. I know that binning in LEDs is a huge issue for certain applications. Do you guys have a role to play in helping improve that binning issue over time?
Absolutely. So with the LEDs, in terms of the binning issue, what you will find is majority of the performance of the LED is determined by the deposition of the stack. And that's an MOCVD process. We don't directly play in that. But what you will find out is you can further enhance the performance of the LED. For example, uniformity of the etch all the way out to the very, very last bit of the edge of the wafer, because LED devices are so small in size that you want to minimize the edge exclusion so that you can generate as many LEDs as possible out of one wafer. So as a normal challenge, the two things that you will see is an increase in the substrate size. So when I said today most of the LEDs are being produced on 2-inch, very rapidly the industry has already moved. Some people have made the jump directly from 2-inch to 6-inch, Some have gone from 2 to 4 to 6. But clearly there is a shift in wafer size. Companies are already going for larger substrates, and they're almost on the same path as the silicon world was, in the sense that with the larger substrate sizes, then you go into single wafer handling, you get into repeatability, better repeatability, low defect rate, and so forth.
You guys do a lot of R&D, presumably, internally, and you leverage R&D from industry sources, from colleges. And when we talk about industry sources, it's been a while since I checked in with Semitech, but those guys are still doing doing the Lord's work, as they say. Yeah. What are some of the challenges that they've identified in your particular space that you're kind of jointly working on for the next generation of tools?
Sure. So that's another unique thing about us, is that we actually define R&D as a target market. So if you look at our market segmentation, we have wireless and LED and number of these markets, but then one market segment is called the R&D market. And there we specifically target larger research institutes all the way down to smaller development centers within a university environment. The reason why we segment it separately is because that's an important market for us, not only from revenue perspective, but also from a partnership perspective. The fact that we work continuously with universities allows us to get sort of a look ahead of time in terms of what else is coming down the road. So we were aware of carbon nanotubes, for example, way before the market became so interested in it. And we were already working with a number of universities where they had our equipment, and they were doing some of the development work on our equipment. And that's just one example. Some of the things that we're working on today, you were referring to earlier about power electronics in electrical vehicles. That's definitely a market that we see a significant increase in. We see definitely a lot of interest from the market. And that is a different device. It has, the device structure is different, the device materials are different, and as a result of that, the requirements for the etch and deposition are different. And we've been very active in that area. A good example of that is etching materials, etching gallium nitride without causing damage, etching very, very thin layers, 10, 20 angstroms of gallium nitride in a very controllable way, so that it's repeatable, that you're etching that exact amount every time that you're etching a wafer, and you're etching it with such low energies that you're not causing damage underneath.
How are you innovating that? How are you able to do that, right? Because the pressure is always there to do things faster, to do things with much more precision. Presumably you can wring some productivity out of software, but there are mechanical, chemical issues you have to deal with too.
Right, so if you look at our workforce, again, referencing some of the earlier conversation we were having, we don't have only material science people. We have material science and electrical engineering and mechanical engineering and software, and very often all of those disciplines have to come together and work as a team in order to develop that next step or that next technology. So in some cases, the innovation could be as simple as developing a new endpoint algorithm, where we use spectrometers to monitor the plasma, and based on the species in the plasma, we can measure how long the etch has gone or how deep we've gone in the etch, and be able to stop the process. That's one way of adding more accuracy to our tool set. So it's integrating other technologies onto our products. That's just one example of those. And then we innovate in relation to that. Then again, we innovate in terms of, okay, so here's the endpoint system. Now let's go find out all these mathematical algorithms that will simulate that endpoint and detect it repeatedly every time.